Okay, so we want to talk about integrals, Lyapunov functions, and Lyapunov curves. Lyapunov was a Russian mathematician in the 19th century, I think. And so that's why that word is there. So what we've been finding when we're dealing with nonlinear systems is we've been finding curves, often lines, that solution curves can cross in only one direction. And this is a very useful way to think about and how to analyze nonlinear systems. With the separatrices, they create regions where all the solution curves behave essentially the same way. So here's the predator-prey system. We've got a null line here where x prime equals 0, and a null line here where y prime equals 0. And then we know that this here is a solution curve coming out of that, and this is a solution curve going into the equilibrium at the origin, another solution curve coming out, and another solution curve coming in. So these are separatrices. They're solution curves, often connected to equilibria, and they block off all other curves, right? Solution curves can't cross other solution curves. And so in particular, these four solutions together with the equilibrium at the origin say that if you start in a particular quadrant, you have to stay in that particular quadrant. We also have, in the first quadrant, we have this line and its equilibrium where x prime equals 0. You have to cross this line going up over here and going down over here. And so that puts a lot of restrictions on what your solution curves can possibly do. Likewise, this null line and this null line have to cross going this way or have to cross going this way. So between the separatrices and the null lines, for example, in this particular box here, there's not a whole lot that can happen. You can't leave this box by crossing the separatrices. You can only enter the box across here, and you can only leave the box across there. And you can't stay in the box because there's no equilibrium in the box. There's an equilibrium over here. So you have to go in and go out, right? And so being able to find these sorts of things helps us a lot with what solution curves are. Even over here, we have a null line over here. You cross it going up. If you start somewhere in the second quadrant, you go up and you cross this. And once you cross that, you can't come back down because you can only cross this line going up. So once you cross this, you go up and you continue going up. So these sorts of curves are really useful to find. And we see null lines and separatrices. And we saw the integrals, right? Integrals give us particular solutions. If I know that this is a solution, for example, which I did by finding the integral for this predator-prey solution, if I know that's a solution, then I know that if you start inside of this solution, you're stuck inside of it. You can't leave because you can't cross the solution. Likewise, if you start outside of that solution, you're stuck outside of it. You can't cross that solution. So curves that are solution curves are really useful because you can't cross solution curves. Curves that can be only crossed in one direction are also really useful. So integrals, Lyapunov functions, Lyapunov curves. And let me say that this is not standard terminology. I don't know a phrase for this, like the null lines. I just call them Lyapunov curves. You won't find that in the literature. So an integral is a function whose level curves are solution curves of the system, like the predator-prey system. Lyapunov functions have level curves which are crossed by the solution curves in only one direction. I'll do some examples of those. And Lyapunov curves are curves, either bounded or bounded, which are crossed by solution curves in only one direction. Null lines, for example, are Lyapunov curves because we know that the solution curves cross only in one direction. So we'll do integrals first, and then we'll do Lyapunov functions and Lyapunov curves. So if we have a system of differential equations, and I'm not going to specify the dimension or anything, and y of t is a solution curve. So a function is an integral of the system if the function I evaluated on a solution curve is constant, right? So Why are they called integrals? Well, let's look at an actual integral from calculus 1. dy dt equals 3t minus 1, right? And we know how to solve that. I mean, formally, you integrate both sides and you get y equals t cubed minus t plus c. So what's our integral? Well, the plus c from calculus now is saying, well, y minus t cubed plus t is a function of two variables, y and t, and it is the solution curves are the curves where this particular function is constant, the level curves of this particular function. So integration, the plus c serves as a way to tell us that we're looking for the level curves of a particular function. So y equals 3t squared minus 1 should be t cubed minus t plus c. But you could think of it as y minus t cubed plus t equals c. And so if we go to GeoGebra, of course, there's a solution. But we can think of it as being a constant. In this case, I'm calling it a equals y minus x cubed plus x. And as we vary a, what do we get? Well, of course, we're just moving x cubed minus x up and down. Right? So these are the level curves of the integral y minus x cubed plus x equals a constant. If we look at this in 3 dimensions, we can graph our function. Z equals y minus x cubed plus x. That's this blue sheet here. And we can take a plane and run it up and down the blue sheet, right? And the intersection is the level curves. Those are the solutions that we have. So y equals x cubed plus x plus c. So we call them integrals because they're essentially the integrals that you see in calculus 1, or you might want to think of the integrals in calculus 1 as specific types of integrals from differential equations. So if we go back to our system, we can look at separable equations. Dy dt equals e to the y sine t. We can rewrite this as e to the minus y dy equals sine t dt. Integrate both sides as we traditionally do for differential equations, and you get, for separable equations, and you get minus e to the minus y equals minus cosine t plus c, or cosine t minus e to the minus y equals c. And so this is my integral. And so the solution curves to this equation, dy dt equals e to the y sine t, should be the level curves of this function. And so we can go to our, back to GeoGebra, find it, and we can change our function now. We want our integral to be cosine of x minus e to the minus y. And there we get a bunch of solutions. And we can let the constant change, and you get this sort of thing. And then you get that, a bunch of asymptotes, and then it disappears. Why does it disappear? Well, when a gets too big, right, this equation is essentially cosine x equals e to the y plus 2.45, right? And so e to the minus y plus 2.45. So cosine x has to be only between 0 and 1. And so when a gets too big, you don't get any level curves at all, right? So if I could actually get it to just stop at 1, which I'm having trouble doing, right, there's where it actually would stop. So if we go to the surface and look at what that looks like. Cosine of x minus e to the minus y. It's a surface that looks like this. If we let our plane go up and down, it's too high up, there's no solutions, and then you get solutions there. They come together. And so the surface is the surface of the integral. The level curves are the black lines, and you can see what the solutions look like. So we'll pause that, go back to our nonlinear systems page. And finally, we have a linearized system at an equilibria, which is this. I should have put in here linear systems. So generally, linear systems, you can find equilibria, except it's kind of a pain. So if I start with dx dt equals ax plus by, and dy dt equals cx plus dy, then I can form dy dx like I did in the predator-prey example as being dy dt divided by dx dt, which is cx plus dy over ax plus by. And then at this point, I'm actually going to do something that seems a little strange. I'm going to factor out an x. Like this. And so I get c plus d times the quantity y over x over a plus b times the quantity y over x. And here we can actually do a substitution. I'll set y over x equal to u, which is the same thing as saying y equals ux. Now, to substitute into a differential equation, I need to be able to substitute not only for the y over x on this side, but I also need to make a substitution for dy dx. And that's why I have this. We're assuming u is some function of x, dy dx equals d by dx of u times x, and now that's a product. So that's going to be derivative of the first times the second plus the first times the derivative of the second, but dx is just x. So dy dx is actually can be rewritten like this. And so with those two substitutions, I can rewrite my differential equation, right? I can rewrite the equation up here as x du dx plus u, right? That's what dy dx is equal to, equal c plus du over a plus bu. That's this up here. This, as it turns out, is a separable equation. Subtract a u from both sides, and that can be rewritten as minus the quantity after you find a common denominator and all that kind of stuff. This is where I say algebra left to the viewer. We can write it like that. Okay. So I can now separate this. A plus bu over bu squared plus A minus du plus c, oops, minus c. Undo. Let's move that cursor down somewhere. Minus c du equals minus dx over x. And then you integrate both sides and you get an integral, right? Because you get something on the left-hand side equals minus log x plus c. On the right-hand side, you solve for c, and then there's your integral. Of course, this is a pain to actually do with this notation because, you know, with all these letters floating around, it would just be kind of grim. And there's 3 different cases depending on whether or not you have 2 real distinct eigenvalues, 2 real distinct, 1 repeated, or 2 complex eigenvalues, basically what happens down there. And if you remember Calc 1, this leads to a bunch of trig substitution integrals. So here's a case that's a little bit easier to deal with. Suppose we have, from the predator-prey example, we have this linearized system, and we want to show that, what do the solutions look like? So in this case, dy dx is dy dt, which is minus 12x over 2y, because that's dx dt. So it's minus 6x over y. I don't need to do the whole substitution with u thing here because I can just separate it directly. It becomes y dy equals minus 6x dx. And we can integrate both sides. You get 1/2 y squared equals minus 3x squared plus c, or 3x squared plus 1/2 y squared equals c. And with a little bit of tidying, we can divide both sides by 3. Plus y squared over 6 equals c. And we know what this is. This is an ellipse. Right? 1 here, and then root 6 is the length vertically. And if you vary c, you get a nested collection of those. So linear systems with purely complex eigenvalues have ellipses as solutions. Now, of course, the predator-prey didn't have ellipses, but that's because it was nonlinear. And the ellipses got distorted because of the nonlinear factors. And we can, of course, go and look at this on GeoGebra. Where's my GeoGebra? There it is. If we put in our function x squared plus y squared divided by 6, oops, not quite right, divided by 6, and we get a paraboloid of some sort, ellipsoid, I guess. And if we let our plane go up and down, we just get a bunch of ellipses, right? And so if you have a center, this is what your solution curves will look like. And hopefully this will come back up from there. And there's our center. And we can go back here and do the same thing. Constant equals x squared plus y squared divided by 6. We have that. We let a change, we just get more and more ellipses, right? And these are the solutions to that system of equation. And then, of course, if there's If A goes negative, there's actually no solution to that. No real solution anyway. And so we have nothing. So you can think of this as a bifurcation diagram where that solution just suddenly pops out of nowhere. Okay, so that is a little bit about integrals.